The other trigonometric functions. In the previous section, we defined the sine and cosine functions as ratios of the sides of a right triangle in a circle. Since the triangle has 3 sides, there are 6 possible combinations of ratios. While the sine and cosine are the 2 prominent ratios that can be formed, there are 4 others, and together they define the 6 trigonometric functions: tangent, secant, cosecant, and cotangent functions. For the point xy on a circle of radius r at an angle of theta, we can define 4 additional important functions as the ratios of the sides of the corresponding triangle. The tangent function, tangent of theta equals y divided by x. The secant function, secant of theta equals r divided by x. The cosecant function, cosecant of theta equals r divided by y. And the cotangent function, cotangent of theta equals x divided by y. Geometrically, notice that the definition of tangent corresponds with the slope of the line segment between the origin 0, 0 and the point xy. This relationship can be very helpful in thinking about tangent values. You may also notice that the ratios defining the secant, cosecant, and cotangent are the reciprocals of the ratios defining the cosine, sine, and tangent functions, respectively. Additionally, notice that using our results from the last section, tangent of theta equals y divided by x equals r sine of theta divided by r cosine of theta equals sine of theta divided by cosine of theta. Applying these concepts to the other trig functions, we can state the reciprocal identities. The other 4 trigonometric functions can be related back to the sine and cosine functions using these basic relationships. Tangent of theta equals sine of theta divided by cosine of theta. Secant of theta equals 1 divided by cosine of theta. Cosecant of theta equals 1 divided by sine of theta. Cotangent of theta equals 1 divided by tangent of theta equals cosine of theta divided by sine of theta. These relationships are called identities. Identities are statements that are true for all values of the input on which they are defined. Identities are usually something that can be derived from definitions and relationships we already know, similar to how the identities above were derived from the circle relationships of the 6 trig functions. The Pythagorean identity we learned earlier was derived from the Pythagorean theorem and the definitions of sine and cosine. We will discuss the role of identities more after an example. Example 1. Evaluate tangent of 45 degrees and secant of 5 pi divided by 6. Since we know the sine and cosine values for these angles, it might make sense to relate the tangent and secant values back to the sine and cosine values. Tangent of 45 degrees equals sine of 45 degrees divided by cosine of 45 degrees equals square root of 2 divided by 2, all divided by square root of 2 divided by 2 equals 1. Notice this result is consistent with our interpretation of the tangent value as the slope of the line passing through the origin at the given angle. A line at 45 degrees would indeed have a slope of 1. Secant of 5 pi divided by 6 equals 1 divided by cosine of 5 pi divided by 6 equals 1 divided by negative square root of 3 divided by 2 equals negative 2 divided by square root of 3, which could also be written as negative 2 multiplied by square root of 3 divided by 3. Just as we often need to simplify algebraic expressions, it is often also necessary or helpful to simplify trigonometric expressions. To do so, we utilize the definitions and identities we have established. Example 2. Simplify secant of theta divided by tangent of theta. We can simplify this by rewriting both functions in terms of sine and cosine. Secant of theta divided by tangent theta equals 1 divided by cosine of theta divided by sine of theta divided by cosine of theta. To divide the fractions, we could invert and multiply. equals 1 divided by cosine of theta multiplied by cosine of theta divided by sine of theta, canceling the cosines, equals 1 divided by sine of theta equals cosecant of theta. By showing that secant of theta divided by tangent of theta can be simplified to cosecant of theta, we have, in fact, established a new identity, that secant of theta divided by tangent of theta equals cosecant of theta. Occasionally, a question may ask you to prove the identity or establish the identity. This is the same idea as when an algebra book asks a question like, show that x minus 1 squared equals x squared minus 2x plus 1. In this type of question, we must show the algebraic manipulations that demonstrate that the left and right side of the equation are in fact equal. You could think of a proof to the identity problem as a simplification problem where you know the answer. You know what the end goal of the simplification should be, and you just need to show the steps to get there. To prove an identity, in most cases, you will start with the expression on one side of the identity and manipulate it using algebra and trigonometric identities until you have simplified it to the expression on the other side of the equation. Do not treat the identity like an equation to solve. It isn't. The proof is establishing if the two expressions are equal, so we must take care to work with one side at a time rather than applying an operation simultaneously to both sides of the equation. Example 3. Prove the identity 1 plus cotangent of alpha divided by cosecant of alpha equals sine of alpha plus cosine of alpha. Since the left side seems a bit more complicated, we will start there and simplify the expression until we obtain the right side. We can use the right side as a guide for what might be good steps to make. In this case, the left side involves a fraction while the right side doesn't, which suggests we should look to see if the fraction can be reduced. Additionally, since the right side involves sine and cosine and the left does not, it suggests that writing the cotangent and cosecant using sine and cosine might be a good idea. 1 plus cotangent of alpha divided by cosecant of alpha equals 1 plus cosine of alpha divided by sine of alpha, all divided by 1 divided by sine of alpha, equals 1 plus cosine of alpha divided by sine of alpha multiplied by sine of alpha divided by 1 equals 1 multiplied by sine of alpha divided by 1 plus cosine of alpha divided by sine of alpha multiplied by sine of alpha divided by 1 equals sine of alpha plus cosine of alpha. Notice that in the second step, we could have combined the 1 and the cosine of alpha and sine of alpha before inverting and multiplying. It is very common when proving or simplifying identities for there to be more than one way to obtain the same result. We can also utilize identities we have previously learned, like the Pythagorean identity, while simplifying or proving identities. Example 4. Establish the identity cosine squared of theta divided by 1 plus sine of theta equals 1 minus sine of theta. Since the left side of the identity is more complicated, it makes sense to start there. To simplify this, we will have to reduce the fraction, which would require the numerator to have a factor in common with the denominator. Additionally, we notice that the right side only involves sine. Both of these suggest that we need to convert the cosine into something involving sine. Recall, the Pythagorean identity told us cosine squared of theta plus sine squared of theta equals 1. By moving one of the trig functions to the other side, we can establish sine squared of theta equals 1 minus cosine squared of theta, and cosine squared of theta equals 1 minus sine squared of theta. Utilizing this, we now can establish the identity. We start on one side and manipulate. Cosine squared of theta divided by 1 plus sine of theta equals 1 minus sine squared of theta divided by 1 plus sine of theta equals 1 minus sine of theta multiplied by 1 plus sine of theta divided by 1 plus sine of theta equals 1 minus sine of theta. We can also build new identities from previously established identities. For example, if we divide both sides of the Pythagorean identity by cosine squared, which is allowed since we've already shown the identity is true, cosine squared of theta plus sine squared of theta divided by cosine squared of theta equals 1 divided by cosine squared of theta. Cosine squared of theta divided by cosine squared of theta plus sine squared of theta divided by cosine squared of theta equals 1 divided by cosine squared of theta. 1 plus tangent squared of theta equals secant squared of theta. Identities. Alternate forms of the Pythagorean identity. 1 plus tangent square of theta equals secant square of theta. Cotangent square of theta plus 1 equals cosecant square of theta. Example 5. If tangent of theta equals 2/7 and tangent is in the third quadrant, find cosine of theta. There are two approaches to this problem, both of which work equally well. Approach 1. Since tangent of theta equals y over x and the angle is in the third quadrant, we can imagine a triangle in a circle of some radius so that the point on the circle is -7, -2. So y divided by x equals -2 divided by -7 equals 2/7. Using the Pythagorean theorem, we can find the radius of the circle. -7 squared plus -2 squared equals r squared, so r equals the square root of 53. Now we can find the cosine value. Cosine of theta equals x divided by r equals -7 divided by the square root of 53. Approach 2. Using the 1 plus tangent squared of theta equals secant squared of theta form of the Pythagorean identity with the known tangent value, 1 plus tangent square of theta equals secant square of theta. 1 plus 2/7 squared equals secant square of theta. 53 divided by 49 equals secant square of theta. Secant of theta equals plus or minus the square root of 53 divided by 49 equals plus or minus the square root of 53 divided by 7. Since the angle is in the third quadrant, the cosine value will be negative, so the secant value will also be negative. Keeping the negative result and using the definition of secant. Secant of theta equals negative square root of 53 divided by 7. 1 divided by cosine of theta equals negative square root of 53 divided by 7. Cosine of theta equals -7 divided by the square root of 53 equals -7 multiplied by the square root of 53 divided by 53.